Welcome back, everybody. Well, now we've spent a few days thinking about how we can use parametric equations to describe how a point is moving around the plane. Today, we're going to start thinking about a new way that we can describe the points in the plane themselves. And to start off, I've got a bit of a doozy here for us. Where is the point -2, 2 over here in our plane? It feels like a trick question, but it's not. It's right here, right? That's where this point lives, right? And when we see a set of coordinates like this, right, it's just ingrained in us that these two numbers have a certain meaning, right? This number on the left is telling us the horizontal position of our point, right? We normally label this with the letter X. And this number over here, this is telling us the vertical position of our point, and we normally label that Y, right? And these are kind of our standard coordinates. We will usually refer to these as rectangular coordinates, since you're talking about just moving horizontally and vertically, or Cartesian is another name that's used, Cartesian coordinates. These are how these numbers are interpreted and how we use these to get our point, right? Horizontal position -2, vertical position 2, there's our point. And the starting place for us today is this idea that while this is one way that we can use numbers to pick out a point in the plane, there are other ways to do this. We can get the same point using other numbers with other interpretations. For example, one way we could do this is if we first picked an angle off of the positive x-axis. And so the idea here is if you maybe can imagine that this positive x-axis here in pink is actually movable. And well, we could kind of move that so that it's pointing in the same direction as our point here. And once we've pointed in the right direction, we just need to know kind of how far up this line do we want to go. And so that's the second piece. We just need to know that distance from the origin to move. And if we give that correct angle and then that correct distance, we're using what's called polar coordinates. And we have some standard letters that we use to represent these. This angle off the positive x-axis, we normally use the letter theta since it's an angle. So up here, this angle we'd call theta. And this distance, we use r. Think about r for radius. And so that is, that's supposed to be straight. There is our r right there, telling us how far to move. And so there's a nice interactive that we have to kind of see this in action. So here is the plane with actually some polar grid lines. And here, I don't know if you can see it in gray, is this kind of arrow that I was talking about. And the idea is, well, if we take our theta, here the measurement's in degrees, but that's fine. We normally use radians, but if we swing that, then our arrow moves along, right? We're setting a certain angle for that arrow to move. And once we've chosen the angle that we like, well then moving this r slides us along this arrow. Right? And if we want to stop at the point right there where we've moved down r equals 4, then this is where we would end up, and this is the point that we would be talking about in the plane. And so we can use an angle and this distance r to give an address or a set of coordinates to points in the plane, just like we can with our kind of more standard rectangular coordinates. Well, let's go back and let's see what the polar coordinates for our point here that we picked out at the beginning are. And so here we just need to find these two numbers here, the angle and the r. And well, here, since we have 2 and -2, right, that's going to be some multiple of pi over 4, or 45 degrees. Right? That would be 45 degrees, or pi over 4 would be even y equals x. So here, this is going to be not pi over 4 or 2 pi over 4, but 3 pi over 4 is going to be our theta. And we do generally write these in radians. All right, so that gets us pointed the right direction. Well, how far out do we want to go? Well, we can actually draw in a nice little triangle here. A nice right triangle. Right, we moved out 2 to the left and up 2, so we actually know 2 sides, and we can use Pythagorean theorem to get us the third side. All right, through Pythagorean theorem, our r squared is going to equal 2 squared plus, we'll just say -2 squared because it'll take care of the sign. And so taking the square root of both sides, this r is going to be the square root of 2 squared plus -2 squared, which is root 8. And so putting those together, we have our polar coordinates for our point. So the r is root 8, and the theta is 3 pi over 4. Right, and so root 8 is about 2.8-ish. 3 pi over 4 is 135 degrees. We can see this now, check it out with our interactive here. We can't see exactly 135 just because of the restrictions on the theta here, but we'll get kind of close. And then, so 2.8-ish for our r. Right there is the point that we've picked out. And notice, just eyeballing it, it's pretty close to -2, 2 in rectangular. Right? And so that's the whole idea with these polar coordinates and how they work. I want to give you a chance to play with doing a bit of translating. So moving back over here, why don't you take a minute and see if you can take this xy point and write it in polar, and then take this polar point with these polar coordinates and see if you can find rectangular coordinates for it. Pause the video, take a minute, and see what you can get. All right, well, let's talk about this. So our point 1, 3 here in the xy plane, right, is going to live about right there. So here's our nice triangle we can draw. We went over 1 and went up root 3, which is, I think, close to 1.7-ish. And so, right, the two numbers we need to know the angle, and we need to know the r, that distance out from the origin. Right, and just like before, r we can find using Pythagorean theorem. R is going to be root 1 squared plus root 3 squared. So we get root 1 plus 3, which is root 4, which is 2. So that's nice and clean. And what about for the angle? Well, here we know the opposite and adjacent side. We can actually use inverse tangent to take that information and spit us out the angle. So inverse tangent is going to take, let me write it like this rather, to start. Tangent of theta we know is going to give us root 3 over 1. And so inverse tangent of root 3 over 1 is going to hand us our angle. And we could either crank this into our calculator and hope for the best, but we can actually see this as one of our favorite angles. A little trick to help us see what might be going on is if we divide numerator and denominator by 2, we're essentially asking, well, hey, what's the angle whose tangent is root 3 over 2 over 1/2? Or in other words, whose sine is root 3 over 2 and whose cosine is 1/2. And this is the angle pi over 3. Or in other words, 60 degrees. And so here are the polar coordinates r and pi over 3 for our point 1 root 3. All right, but what about the point 3 negative pi over 2 in rectangular? Well, let's actually go back to the interactive. So if we kind of reset the arrow here, go back to angle 0, negative pi over 2 is negative 90 degrees. So that's actually going to swing us down, clockwise. There's negative 90 degrees, negative pi over 2. And we want to move out 3 for r. So that's going to push us just down along that negative y-axis, right, down to the point negative 3, 0. So in rectangular, we get at this point xy coordinates are, I guess it would be 0, negative 3. I think I said it in the opposite order just a second ago. But the x coordinate 0 and the y coordinate is negative 3. Yes. But now, something interesting that happens with polar coordinates that doesn't happen with rectangular coordinates is that there are actually a lot of different polar coordinates that we can give for a particular point. And this essentially comes from the fact that as we swing our arrow around, it's going to eventually wind up pointing the same direction. So for example, if we wanted to get this same point in red a different way, well, let's just take our angle and let's maybe swing it counterclockwise until we are facing that same direction. So if we do that, just go around the circle again. We're right back where we started, but we have a different angle. Essentially what we've done is we've taken our old angle, negative pi over 2, and we've added 2 pi to it. Or here, we took negative 90 degrees and added 360 to get back to the exact same point. Right? And this interactive won't allow us to do it, but we could keep on going. Right? We could go around the circle again and again and again in either direction. And so we actually have infinitely many ways to write that point. That brings us to this note down here. So here, this was our r equals 3, and when we added two pi to our pi over 2, we get, to the negative pi over 2 that we started with. All right, and then we could add 2 pi again. We could start with negative pi over 2. We could subtract 2 pi, and we can do this any number of times. And so kind of all possible ways to do it with this positive radius of 3, we can write as taking our starting angle that we used and just add any integer multiple of 2 pi. So we can write 2 pi k. Those will all give us the same point. Now you've possibly been wondering, as we've been doing the interactive, what happens when we take the r and slide it negative, and we do indeed allow this. So for example, another way to get our point down there is, well, what if we point our arrow up at 90 degrees, pi over 2, but now we slide our r into the negatives, and if we bring it to negative 3, then we'll get that same point. And so we do indeed allow for negative r's with polar coordinates, and that'll just move us in the kind of backwards direction from where our big arrow is pointing. And that's actually the reason why I put distance in quotes on the first page of our notes, just because r can be positive or negative. So moving back to our note page, we can get that same point by going to positive 90 degrees and then making r negative 3. And again, we can then move forward or backwards around the circle as many times as we want. I'll just show one of those. All right, so if we start here and maybe decrease our angle, then if we just do it enough, we'll wind up back at the same point, right? And we could keep going if the interactive here would allow us. The next note I want to make is that to get the origin right here, the point 0, 0 in rectangular, we just want to let r be 0. And once r is 0, it actually doesn't matter what our angle is. We'll always be getting the origin. And so here we can write the origin as r equals 0, and doesn't matter what theta is. Next, I want to talk about relationships between our rectangular and our polar coordinates. And we've really been using these already when we were doing our translating back on page 1 of these notes. And so I want to capture these formulas so that we have them on hand. And really, where they come from is just our nice, clean triangle that we can draw. If we have a point here in the plane, it's got rectangular coordinates, it's got polar coordinates. And once we draw this nice right triangle, we can add to the sides here and the angle all 4 of these coordinates. For example, x is going to be this adjacent side, I guess adjacent to our angle. Okay? That's where theta lives. Y is the opposite over here, and r is the hypotenuse. And once we have a right triangle, we have all sorts of stuff we can say. We can toss out Pythagorean theorem. We can toss out our trig stuff, thinking about SOHCAHTOA, and those will all give us useful identities. So for example, right here, we have what Pythagorean theorem tells us. This is a nice one to keep in mind. X squared plus y squared equals r squared. And we could solve that for r, here if we think about r as being positive, it would be the positive square root. Thinking about SOHCAHTOA, cosine is going to be x over r. And so if we multiply both sides by r, we'll have that x is r cosine theta. And similarly, sine is going to be y over r. And so solving for y here, y is r sine theta. And these are real nice translation formulas to keep in mind. Notice that on the right-hand side is all the polar information. We have our r and our theta. And on the left-hand side are our two rectangular coordinates. And so these equations kind of serve the purpose of taking polar information and translating that to rectangular information. All right, our last trig function we could look at, tangent of theta is going to be y over x. And we can use that to find the angle of our xy point using inverse tangent. There is a little caveat though. This does require our point to be in the right half plane like it is here in the picture. If it's not, if our point is somewhere like our -2 point that we started with, where it's in the left half plane, over here, then inverse tangent is actually just going to give us an angle from -pi/2 to pi/2. In this case, it would tell us the angle of, I guess it'd be -pi/4. And we just have to realize that we then have to add pi to be pointing the right direction. So we could say, if not, then we'll add pi to the angle that inverse tangent gives us, so that we're pointing the correct way. All right, and so these are the nice formulas that we want to keep in mind for how rectangular and polar are related to each other. What I'd like to do now is do a little bit of compare and contrast of how these coordinates work and how they look. For example, let's start by comparing what I'll call coordinate equations and regions. And what I mean by coordinate equations are the solution sets that we get when we just take our coordinates for rectangular, just x and y, and set them equal to some number. Right? So here, if we set x equal to some number like 3, well, what sort of curve are we going to get in the plane? That's just going to be a vertical line, right, at x equal 3. Similarly, if we set y equal to some number, that's going to give us just a horizontal line at that y value. And then if we allow a range of x's, so x from a to b, and y from c to d, and ask for all the points that satisfy that, well, then we're going to get this rectangular region. Another reason why these coordinates are called rectangular coordinates. Well, for polar, we don't have x and y, we have r and theta. Why don't you take a minute, pause the video, and see if you can sketch the solution sets of these two equations here, just one at a time, and the region that we get from these inequalities over here. All right, well, let's talk about these. I'm going to actually move over to the interactive for our first two. The first thing I want to mention is that with this equation, r equals 3, because theta is not involved, theta can be anything. Just like up here with our x equals some number equation, right, it was implied, but because y isn't involved, that y can be anything, right? And that's what gives us this whole line. And similarly over here with our theta equation, because r is not specified, r can be anything. Well, let's jump over to our interactive. All right, so if let's kind of reset our arrow here at 0 degrees. If we let our r be positive 3. So this point right here is on our solution set since it has r equals 3. But now what happens, as we let theta vary to anything it wants, if we imagine our point kind of dragging along a red Sharpie, what curve would it be tracing out? Right, the circle of radius 3. So that's the solution set for r equals 3. Well, what about the solution set for negative theta equals negative pi over 6? Negative pi over 6 is negative 30 degrees. And so if we set our angle there, so there's angle 0, negative 30 degrees is right there. And so this point is on that solution set. But r can be anything. And so now if we let r vary to be whatever it feels like, notice we're just going to be moving forwards and backwards along our big line here, our big arrow. And so actually, if we could drag this as far back and as far forward as we'd like, we'd be tracing out the entire line that our arrow is giving us here at that angle. So moving back, here's what I got for our graphs. And so here's our circle of radius 3, and over here, all right, our line here was set with the angle negative pi over 6. And then over here, if we want points that live between that have r coordinates between 1 and 3, those points are going to live between the circle with radius 1 and the circle of radius 3. And if they have theta between negative pi over 6 and negative pi over 2, then they're going to be between kind of this ray here, negative pi over 6, and between this ray, pi over 2. And so putting that together, we'll have this kind of chunk of this Cheerio here. That's the region that these inequalities describe. Okay, so let's look at one more equation today. Here, this one's a little bit more involved. Let's look at the equation r equals 4 cosine theta. And so here the idea is that this is an equation, similar to r equals 3 or theta equals negative pi over 6, but here this involves both of these variables. Now here this will, because it's an equation involving our variables, this will give us a curve, just like we got a curve in these two examples above. But the question is, what is it? Well, there's going to be what I call a main way that we go about figuring out what the solution set to this curve looks like. Right, in general, the solution set is, all the points are theta whose, coordinates satisfy that equation, have r equals 4 cosine theta. And you can think back a little bit to, if we have an equation rectangular like y equals some function of x, we normally would graph that by taking x's and plugging them in, filling it out that way, and that will be more or less our main way of figuring out what this looks like. We're going to play around with this way more next time. We're going to kind of graph what this looks like in the r theta plane and figure out from there next time. But right now, I just want to take a couple minutes and show how we can actually take this polar equation and translate it into a rectangular equation. Now, I have this note that this usually is not going to give us something nice, just because oftentimes things that have descriptions in polar end up being cumbersome to write in rectangular. But in this case, we actually will get something nice, and through translating, we'll be able to see what this looks like. And so the idea here is we want to make use of our translation formulas. And the cleanest way to do that is actually to start by taking our equation and multiplying by r. So that over here on the left, we get our r squared, and over here on the right, we get r cosine theta. And we have formulas for both of these. R squared is x squared plus y squared, and r cosine theta is x. And now, actually, already, if you remember, pre-calc and conic section stuff real well, this is actually an equation for a circle. Already, we know that we're going to get some kind of circle. The question is what one, and we can do a little complete the square action to figure that out. So here, if we take this 4x and bring it over next to the x squared, right, we're going to want to add something to both sides in order to help our x stuff collect. And recall the way that this goes is if our coefficient on x is b, then what we want to add is b over 2 squared. And in this case, b over 2 would be negative 2. Square that is positive 4. And we'll want to add that to both sides to keep our equality. And once we've added that 4, indeed, this x stuff does factor nicely as x minus 2 squared. And right here, right, we can recognize this as the equation for a circle in this kind of standard form. The radius 2 comes from that square root of 4 here. And our center, we can read off the positive 2 from our x bit, and we can think of this y as y minus 0 squared. So that gives us our center. And so here, in this case, translating to rectangular, it's allowing us to see what kind of curve we're getting. Next time, we'll actually see how our main method looks, how we can, in general, take an equation like this, r equals some function of theta, and feel out what our solution curve is going to look like. That's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.